Assalamualaikum and good day to everyone. Now we are going to study on Sieve analysis of fine and coarse aggregate based on BS 882 and ASTM C136. Now, the objective of this testing is number 1, to determine the particle size distributions of fine and coarse aggregate. Number 2, to study how to perform the sieve test. Number 3, to plot the graph using the experiment data. And the last one, to describe the aggregate sample based on particle size distribution curve. Therefore, at the end of this lecture, the expected outcome, students should be able to describe the suitable aggregate properties for concrete mix design. Let's start how to prepare the laboratory report. So here, you must have cover page. Why? Because cover page consists of experiment title, date of experiment, group number, who is the person in charge. Alright, next, you will study how to write the introductions of the topic. For this example, today we're going to study what you should write under your introduction to aggregate. Next, the objective of the testing. Okay, so number 3, what is the apparatus you need to write or you need to report that you need to use? Okay, and then the flow of the experimental. What is the procedure? You need to present your flow chart. And then number 5, result. How you present your result? So we will go through today. And then the discussions and analysis, and then after that you need to prepare the conclusion. And then number 8 and number 9, you need to include any appendix or reference that related to the experimental title. Here is introduction on sieve analysis of fine and coarse aggregate. Number 1, this test is used to determine the gradings of material that are to be used as aggregate. It ensures that particle size distributions complies with applicable requirements and provide the data necessary to control the material of various aggregate products and mixture containing aggregate. And then number 2, aggregate is one of the basic constituents of concrete. Its quality is of considerable importance because about 3/4 of the volume of concrete is occupied by aggregate. So, one of the physical properties of aggregate that influence the property of concrete is the grading of aggregate. So, the gradings of aggregate defines the proportions of particle different size in the aggregate. So, the aggregate of fine size below than 5 mm and the coarse aggregate size is more than 5 mm. Next, under the introduction, you may also include related theory to the experimental title. Alright, so number 1 here we have fineness modulus. So what is the fineness modulus? So here, fineness modulus, FM, tell us directly whether the material is well graded or gap graded. And then, fineness modulus value can describe whether the material is fine or coarse. So, how to measure the fineness modulus? So, here we have the range of fineness modulus. Higher the value of FM, coarser will be the aggregate. Here is the range, 5.5 to 8. And then, For good fine aggregate, FM should be between 2.3 and 3.1. And then the finest modulus between 3.5 to 6.5 is for all in aggregate. So what is the formula? So here, this is the formula of FM. Here is the FM is equal cumulative percentage retained on size of 100 mm divided by 100. So where to get the cumulative percentage retained? So here, after you analyze the experimental data. Next is grading requirement. So this grading requirement can measure the quality of the experimental sample. So here, according to BS or ASTM, there are limiting values for every sieve that used as a reference to indicate the quality of sample. So here, you need to plot the curve of minimum and maximum value provided by BS or ASTM. Then you can plot a curve of the samples of the experiment. And then, so this is the description. If the curve of sample material lies inside the both minimum and maximum curve, then the quality of sample is good. So next, if curve of the specimen material or sample material lies outside the both minimum and maximum curve, then the sample is not according to the specification. Here is the grading limit. So here is for the fine aggregate, and this table is for the coarse aggregate. So this is the sieve size. So this is the range of sieve size is from 9.5 mm to 150 mm. And then here is the minimum or lower limit, and this is the maximum or upper limit for the fine aggregate. So you need to plot these both data in the graph. So let's say your experimental data lies in between this limit, then the specimen sample is good. So here, this is the coarse aggregate limit. So here you have the size below than 37.5, and here size below than 19 mm, and here the size of coarse aggregate below than 12 mm. So here you have minimum and maximum, and this is also minimum and maximum, and this one is minimum and maximum for 12.5. So as usual, you need to plot this value into the graph respectively. Here, this figure illustrates the gradings of the specimen experimental, which is fine natural aggregate according to the ASTM C33. Upper and lower limit. So what we can see about this graph, so the bold line here is the upper and this is the lower limit, and then the dotted line here is represent the curve of the specimen. So the specimen here is the natural fine aggregate. So what we can say about this grading? So we can say that the gradings of this specimen material, or this is the natural fine aggregate, fall within the range of the upper and lower limits of the ASTM C33, and this material meet the gradation requirement. Here, this graph illustrates the gradings of the natural coarse aggregate according to the ASTM C33. So what we can say about this specimen? So the dotted line here is the coarse aggregate. So here, this curve represent within the range of the specification for the size for the 10 and 20, right? Because the size for 10 and 20 is within the upper and lower limit. But what is for the 5 mm? You can see here, the 5 mm coarse aggregate was out of the boundary here. So here, based on the curve, we can say that this is the gap graded of the gradation. So, can we use this specimen, or is this specimen is good and meet the requirement of ASTM or not? Here is the particle size distribution curve. So the number one about well-graded aggregate. So these figures illustrate the well-graded aggregate for the fine and for the coarse aggregate. So what is the definition for the well-graded aggregate? So this figure illustrates that well-graded contains of small particles and coarser particles of the aggregate. So what is the importance of this well-graded aggregate? So here, well-graded aggregate concrete mix will fill more of the voids between the coarse aggregate and reduce the amount of locking between the coarse aggregate. And then this both reduce the amount of cement required to fill the void and improve the workability of the concrete mix. So that is why we need to do the grading curve. So how to plot the grading curve is from the sieving analysis. Next, gap graded curve. So here you may refer to this figure. So this figure presents the gap grading. So what is the gap grading? Gap grading refer to one or more intermediate size are omitted. So for this example, so this figure show that there is no size for this particle between 10 to 2.36. So that is, we call it a gap graded. So you may refer to this figure. So this is the examples of the gap graded. Gap graded means that you only have coarse aggregate and fine aggregate. So you don't have the intermediate size. So gap graded aggregate consists of coarse aggregate particle. They are similar in size but significantly different in size from the fine aggregate. So what will happen if we have this gap graded aggregate? So the smaller particle could easily enter the void, so that the workability of the mix would be higher. And then this graded, prone to segregation. And then graded concrete is difficult to pump due to the segregation. And also, a gap graded aggregate mix will lead to reduced workability, greater water and cement requirements, and can lead to excessive bleed water. And then gap graded fine aggregate can also lead to excessive bleeding and reduced fishability. So you must avoid this gap graded aggregate. Here is the third graded curve. It is poorly graded aggregate. So you may refer to this figure. So this figure represents fine aggregate and coarse aggregate poorly graded. So what is the meanings of the polygraded? So polygraded aggregate categorized by small variation in size which the proportions of certain intermediate particles are not enough. This means that the particle packed together, leaving relatively large voids in the concrete. So how about the S shape? So the S shape is too steep. It is uniform, but it is very steep. So that is we call polygraded aggregate. So you also may refer to this figure. So meaning that this polygraded doesn't have enough for the intermediate size. So what will happen to the concrete? So here, polygraded aggregate used in concrete will contain a higher volume of void which must be filled by cement. So it's become uneconomically. And then more paste in the concrete mix will lead to higher shrinkage and higher cost. And then polygraded aggregate in concrete also increases the surface area of aggregate which must be coated in cement paste in order for the mix remain sufficiently workable. And then polygraded aggregate in concrete also increase the risk of concrete being more difficult to finish and increase the likelihood of segregations during compaction. Here, the objective of the testing. So number 1, to produce grading curve for fine and coarse aggregate according to BS and ASTM. Number 2, to determine a good distribution of aggregate. So we have go through the grading curve. We have 3 types. So we have well graded, we have gap graded, and then we have polygraded. Here is about the apparatus and test specimen. So here we need to have balance of scale that we need to weigh the specimen and also this pen. So this pen we have 2 sets. First set is for the fine and second set for the coarse aggregate. And then we need to have the oven. Why? Because we need to oven dry the specimen. And number 5 is the mechanical sieve shaker. So why we need sieve shaker? Because we need to filter, we need to sieving the specimen, or you can do by manually. And then the last one, we need to have the experimental specimen. So here we have coarse and fine aggregate. Here is the procedures of sieving analysis for fine and coarse aggregate. So here, number 1, dry the sample, which is 3 kg fine aggregate or coarse aggregate to a constant weight at temperature 110 or plus minus 5 degrees Celsius for 24 hours. And then number 2, mix the sample homogeneously and form it into cone shape before reducing in 500 grams by using the quarter method. So this is the quarter method. And then number 3, the cone is level and divided into 4 portions equally from 90 angle. And then number 4, the opposite part of the portion is ignored. The other 2 portions is made together before reducing the sample 500 grams. And then, so number 5, a stack of sieve pen is prepared whereby sieve having a larger opening size are placed above the sieve smaller opening. So here, this is the set for the fine aggregate. So here is the size 9.5 to 100 mm. And then for the coarse aggregate, we have the pen size from 118 millimeter to 100 millimeter. So here you need to arrange the pen size. So the pen size need to arrange from the largest to the finest. Okay. So then sieve the sample by shaking using mechanical shaker around 10 to 50 minutes. So this is the example. If we do for the fine aggregate, So the above is the larger size and the lowest part is the final size. Because at the end, you will see like this figure. Next procedure, we need to weight each sieve and the pan with the sand retained or coarse retained on the pan. So we weigh and recorded of the sample retained in the pan for this example. So before that, we need to weigh the empty pan. So after that, we can weigh the pan and retain specimen. So next procedure, we need to prepare table and calculate for the percentage final. In this table, we need to determine what is the mass retained, what is the percentage mass retained, and then we need to calculate what is the cumulative percentage passing. Why? Because the next procedure, we need to plot the grading curve. So the grading curve like this figure. So the x-axis is the sieve opening and the y-axis is the percentage passing. So we are using the log scale. So we can follow the similar procedures or repeated for the coarse aggregate test. Next is the result of the sieve analysis for the fine aggregate. So here this is the tabulate data from the experimental. So first column is about the sieve size and second one is the mass of the sieve, and here mass of sieve plus sample. Then how to determine the mass retained? So you can subtract the mass of sieve pan plus specimen minus mass of sieve. Okay, so you need to do for the rest of the data. And how to determine the mass retained? So mass retained can be determined by you need to sum. You need to sum the sum of the specimen. So this is the mass retained. So the mass retained can be determined by this specimen minus this pan mass of pan. So you will get 2.12 for this example. And then you need to get the percentage mass retained here. Percentage mass retained can be determined by you need to get what is the total of the mass retained here. So we need to get the percentage mass retained is x divided by summation mass retained total times 100. So for this example, we have to get the 0.42, we have 2.12, we have 2.12 divided by 503.8 times 100. So we can get that 0.42 here. And then you can do for all data. Alright. Okay. Next column, we need to get what is the percentage cumulative retained. This one. So this cumulative means that, so the first column, you just write the first column here 0.2. But the second column, the second row, we need to add 0.42 at 0.86. So you will get 1.28. And then how to determine this 7.67? So 7.67 is 6.39 plus 1.28. So you get here. So this one 7.67 plus 11.9, you get 19.57. And then 19.57 at 24.73, you will get 44.3. And then you should do for the rest here. So until you get total is 100. So this is the percentage cumulative retain. So now the last column, we need to get what is the percentage passing. So this one, the first row, we can determine that from 100. So 100 minus 0.42. So we get 19.58. And then we can have that 100 minus 1.28. So we can get that 98.72. And then so on. So here 100 minus 7.67, you get this. And then here 100 minus 90.57, you get 80.43. So until here. So the last one, 100 minus 100 is 0. So now which column versus each column? So definitely we can plot. This is the x-axis and this is for the y-axis. Here, this is the log scale graph. So this is for the x-axis. So x-axis means that the sieve size. And here is the y-axis. So y-axis means that percentage passing. So we need to plot according to the sieve size. So here you may refer to the top of the size here. So here you can have that. We have the 10 mm, and then here we have 5 mm, and then here we have 2.36 mm, and then 1.18, and then here is 600 micrometer, and here 300, and here is 150. So after you plot, then you can have the connection, connect to each of the point here. So what is the curve? What is the shape of this curve? Is it well graded, gap graded, or poorly graded? So here it is the well graded. So why? What is a well graded? Well graded. What we can say as a well graded curve? Because you can say that what is the size? So this is the size, right? So a gradation for this curve have the from finest to the coarsest, and also the S shape show that well graded. So these specimens of fine aggregate is the graded as well graded due to the contains particle from size of this one is 150 to 10 mm. So that is why how we can grading the aggregate. Next, how to determine the properties of the aggregate. So after you identify, characterize the gradings of the aggregate. So for this specimen is the S shape is well graded. Okay, number 2, you can determine the property of aggregate by determining what is the fine modulus. So fine modulus is equal to summations of the cumulative percentage passing divided by 100. So what is the percentage of cumulative passing? So you can calculate, and then you will determine what is the range. Is it fine or a coarse aggregate? And then the third one, you can determine by this one. This is, you can look at the 50%, then you go downward here. So here you can have that this aggregate consists of what? From medium to coarse fine aggregate. Here, this is the second method to determine the percentage of cumulative passing. So after you can determine the percentage of mass retained, So you also can determine the percentage of cumulative passing by minus straightly directly 100 to this 0.42, and then like this example, 100 minus 0.42, you will get the 99.58, and then this 99.58 you direct minus with 0.86, so you will get this 98.72, and then the 98.72 you will minus with 6.39, then you will get 92.32, and then you will do for the rest of the data. So until you get 0 here. Okay, so as usual, you can plot. This is the x-axis and this is the y-axis. This is the shortcut method. Here, this figure illustrates the grading of the specimen falls in between the limit for the upper and lower limit. So this specimen meet the specifications of requirement. So you can plot the graph by using the Excel. You can try by yourself. So is it the specimen is a good or and quality sample or not? Yes, right. Next result is for the coarse aggregate testing. So this data is determined by Sieve analysis of coarse aggregate. So as usual, the first column is the sieve size from 37.5 until 2.36 mm, and the second column is for the mass of the pen size, and then here is the mass of the pen size with the sample, and here you already calculate what is the mass retained. So mass retained can be determined by this pen mass together with the sample minus with this pen size. So you get the mass retained here. And then you can calculate for the rest of the data here. And don't forget to have the summations of the total mass retained, because we need to calculate what is the percentage mass retained here. So the last column is for the percentage passing. So this percentage passing directly get from 100 minus with this, you get this. Okay, 100 minus 0 is 100, and then 100 minus 37.33, you will get this 62.67, and then 62.67 minus 26.11, you get this 36.56, and then you do for the rest. Okay, until you get 0 here. Then you need to plot. This is for the x and this is for the y, and then you need to determine what is the curve shape. Then you can classify, characterize. Is it what is the shape? Can you try to plot? So here, so this is the x, the sieve size, and this is the y, is the percentage passing. So you can plot based on this size. So this for this data of the coarse aggregate is starting with the 37 mm until 2.36. So this is the 2.36 here. 2.36, right? So after you plot, then you have to connect. You can connect the point to each other. All right. So first, so what is the grading curve? So is it well graded, poor graded, or what? Gap graded. So what is the answer? So what is the S shape here? So we can say that it is the poorly graded. Why? Because we have the steep curve. Right. So steep curve means what? So this size, this grading only contain what particle? So it contain this 2.36 until 3.36. 37.5 mm, but does not have enough percentage. So it means that it contains aggregate particles that are almost of the same size. So this means that the particle packed together leaving relatively large voids in concrete. So we can also call it as a uniform graded. Uniform graded. So this one is equal to poorly graded. Right. Here, this figure illustrates that the specimens for the coarse aggregate lies in between upper and lower limit. So we can conclude that this specimen is good quality and it met the requirement. So you can try by using the Excel log scale graph. Next part after result is the discussion. Here, discuss the result whether the fine and coarse aggregate is well graded, gap graded or poorly graded. So based on this experiment, so you obtain that, you determine that, example for the fine aggregate is well graded. Why well graded? Because a gradations of particle size that fairly evenly span the size from the finest to coarse. So it is categorized by the S shape. And then the samples of the fine aggregate is graded as well graded due to it contains particle of wide range of size and has good representations of size. Sieve from number 4 to 200 sieve. And then for the coarse aggregate, what you can discuss for the coarse aggregate. So here, for the coarse aggregate, we determine that poorly graded aggregate based on the steep S curve. So here it contains aggregate particles that are almost of the same size. So this means that the particle packed together leaving relatively large void in the concrete, and that is also called as a uniformly graded. So as usual, based on what your experimental data. So after you getting the experimental data, then you have to tabulate into table, then you can plot the graph, then you can do your own analysis. And then the last part is conclusion. So what is the conclusion? So at the end of the testing, at the end of the experimental, you should be able to get what is the grading curve for the fine and coarse aggregate based on the BS and the ASTM. So definitely the outcome, you need to determine the well graded. So what is the purpose of the sieve analysis is to determine the gradations for the aggregate. So for the best gradation is well graded aggregate. Because of what? Because this well graded aggregate leads to compact and denser of concrete. It consider the best grading because contain all size of particle which lead to lesser quality of cement requirement. So here everyone should know how to characterize well graded, poorly graded, and then gap graded. Okay, that's all for the sieve analysis test. Hope everyone here can perform the sieving test. Thank you. That's all for today.